differential elements. Differential element is nothing but infinitesimally small element. That if you are considering a length, it is infinitesimally small length, then it is called as differential length. If you are considering very small area, it is a differential area. If you are considering infinitesimally small volume, then it is called as differential volume. How to obtain the differential length and what is the application of the differential length? How to obtain the differential surface and what is the application of the differential surface? It's like that we will discuss one by one in all coordinate systems. So what I do is I will start with our rectangular coordinate system. So in the rectangular coordinate system or the Cartesian coordinate system, how the differential length, surface and volume were defined. That what we examine initially. Now the same concept will be applicable to the remaining two. That for that consider a differential volume. That here what I am doing is I am considering a differential box, a small box. Since it is a rectangular coordinate system, a rectangular box was considered. Now we need to observe what is the differential length, what is the differential surface for this particular box and along differential volume also. Now observe, here what we have is different lengths, a differential length in this direction, differential length in this direction, differential length in this direction. That the differential length for this particular direction can be written as, since it is y axis, that is along the y, you can write this one as dy in the direction of y. So the differential element what we are considering in the direction of y is dy ay, that the direction may be like this, right. Next, consider this particular part, thus this differential length is along the x axis. Since it is along the x axis, this can be written as differential length in x axis dx in the direction of x. And the third one what I am considering is this differential length is in the direction of z. So this can be written as dz in the direction of z. So here clearly what we have is three differential lengths for that box. If you consider remaining all, obviously they are parallel and equal to the terms what we discussed, right. This is dy ay and backside you may have another that is also called as dy ay. dx ax, this is also as a dx ax and dz az, this is dz az, this is dz az, right. So here clearly on an average three differential lengths will exist in all the directions called as dx ax, dy ay and dz az. So if you want to write down the differential length equation in x direction, that I am representing this one as differential length in x direction, that is simply dx ax. And if you want to write down the differential length in y direction, that is dy ay. So the general equation for the differential length can be written as dl is equals to, this is a vector, the differential length is represented in a particular direction. So in this direction the length is there, in this direction the length is there. So here clearly the differential length is a vector, the dl bar is equals to, it is dx ax plus dy ay plus dz az. That is the generalized equation for differential length in our rectangular coordinate system. So whenever we require, we need to use this differential length, right. So if you want in a specific direction, just you have to go for this individual formula. Now we will observe differential surface. As I said, differential surface is a quantity which has infinitesimally small area. For an example, consider this differential surface. If you want to calculate the magnitude of this differential surface, that what I have mentioned just now, the differential surface is denoted with symbol ds. This is also a vector. So ds bar is equals to, just write down the magnitude initially. The direction, the magnitude here is dy and the magnitude here is dz. So the magnitude dy dz. But as I said, this is a vector. So whenever there is a surface, we need to represent what is the direction of that particular surface. So if you want to represent the direction of surface, if there is any volume, we need to observe the volume and mention the direction of this differential surface as normal to the surface and perpendicular to the surface and away from the volume. That this simple point you need to remember for any surface. So if we are considering a surface, always the direction is perpendicular to the surface, that is normal to the surface, and if there is any volume, it is away from the volume. If there is no volume, then I will give you. So that initially remember that the direction of our differential surface is always perpendicular to it, right, or normal to it and away from the volume. So here clearly the direction which is away from the volume and normal to this particular differential surface is like this. So with the observation what you can say is the direction is x. So clearly the ds bar can be written in the direction of x as dy dz ax. In the same way, if you want to write down the differential surface, that what I am representing now, that is this grid. For this grid, if you are considering this grid surface, then the magnitude is dx dz. I don't know what is the direction, so just I am writing the magnitude initially. So write down dx dz as a magnitude and recollect the point that always the direction is perpendicular to the surface and away from the volume. So it's a perpendicular to the surface and away from the volume always lies in the direction of y. So this differential surface can be represented in the direction of y, that is dx dy ay. In the same way, if you take the top, that the direction of this differential surface is in the direction of z. So the differential surface, this can be written in the direction of z as dx dy in the direction of z. Right? So every time whenever we are calculating a particular quantity with respect to the surface, or if you are supposed to integrate with respect to that particular surface, we need to calculate the direction of that surface. Since we are considering all the vector quantities, this surface also will be considered as a vector, and with respect to this surface we need to integrate or evaluate a particular quantity. So the observation of direction for this surface is very important. So remember this point, it is always away from the volume and perpendicular to the surface. Now I will give you a simple technique how to obtain this differential surface for a given direction. So no need to go for all this analysis again, just by considering a box and obtaining the magnitude and obtaining the direction which is away from this one. So no need to go for entire thing, just I will give you a simple technique how to obtain the differential surface from differential length. So what you have to do is you have to remember this differential length initially. So if you remember this differential length, the differential surface can be easily obtained. This is applicable for all coordinate systems, not only to the rectangular, applicable for all coordinate systems. So how to obtain that? Now I want differential surface. Initially I need to observe in which direction I want the differential surface. If I want differential surface in z direction, that this is the differential surface in z direction. For that a simple technique is there. In which direction you want the differential surface? Z. So just you close this z term, then multiply the magnitudes of remaining two terms. If we close this term, the remaining two terms are dx and dy. The magnitudes are dx dy and take the direction as z. Since we are taking the differential area in z direction, the direction is z. So same as your previous one. In the same way, the differential surface in x direction, that already we gone that one, so we gone through that one. But now once again just you observe differential surface in x direction with this shortcut. Close this x. If you close this x, the remaining two terms are dy dz and multiply the components dy dz, that is dy dz at the x direction ax. Just a very simple technique which will be useful for getting the differential surface in the required direction. If you want to get the differential surface in minus z direction, no need to go for any other complex analysis again, just the differential surface in minus z direction we want. So the magnitude is same, that is dx dy, but we are considering that one in minus z direction, that the vector will be reversed. It's a minus az here we need to consider. So this is a very simple technique to obtain the differential surface. Now we have one more quantity called as differential volume. What is differential volume? An infinitesimally volume for the box what I am taking, right? So consider the magnitude dy, consider the magnitude here dx, consider the magnitude here dz. So differential lengths, it's a dy dx dz will give us the differential volume. So the differential volume now can be written as simply dv, notation is dv, which is equals to multiplication of all those components dx dy dz. Remember this dy is a scalar quantity, that volume has no direction. The differential length is a vector quantity and differential surface is also a vector quantity, but differential volume is a scalar quantity. That the simple technique to obtain this differential volume, once again No need to remember this expression dx, dy, dz. Just you multiply all these components of vectors dx, dy, dz. That if you multiply this dx, dy, dz, then what we will get is the differential volume, right? So here clearly we discussed about the differential length in all directions, and so whenever we require the differential length, you can consider the corresponding component and the differential surface in a required direction and differential volume for the given coordinate system. Now as I said, if you have a volume, the differential surface has a direction which is perpendicular to it. If you have no volume, only surface is there, then once again just to follow the right-handed thumb rule. That right-handed thumb rule means just you place your folded fingers along the direction of curve, then the direction of thumb always gives the direction of surface. That randomly consider some surface. Let us take this is the surface what we have, and we have no volume here. Since we have no volume, we need to obtain even though we have no volume, we need to obtain the direction of this particular surface. To observe that one, just place the folded fingers along the curve. If you place folded fingers along the curve, the direction of our thumb always gives the direction of surface. That is a normal direction what we need to take like this. So for this plane of board, it is coming out of the board. That gives us the direction of surface. Just you remember this. Now what we do is we will apply the same differential length, surface and volume for the remaining two coordinate systems also. Just we will observe in the cylindrical coordinate system, same as our rectangular coordinate system, in the cylindrical coordinate system also we need to consider a differential volume. So what is the differential volume which can be considered in a cylindrical coordinate system? Just clearly observe what I am drawing. A cylinder with radius rho, or what I am drawing, let us take a cylinder is considered with some radius rho. Now a differential volume for this cylinder I will consider. That clearly examine here. What I am doing is I am taking a small piece in the cylinder. So if you take a small piece within that particular cylinder, just it looks like a piece of cake. If you are taking a cylindrical cake and if you are taking a small piece from that one, just that piece looks like this, right? So this is called as a small piece of cake, and it clearly it is a volume, differential volume what we are considering. Now we need to observe what are the dimensions of this differential piece or differential volume. Now observe, this is in the direction of rho, right? This is in the direction of z, and this arc or the curve what I have drawn is in the direction of phi. So if you want to observe the differential lengths, then we need to consider the differential length along rho, differential length along z, and differential length along phi. So if you are considering differential length along rho, it is very easy, since it is a length, differential length along rho direction, just a small part of this one, that is d rho in the direction of a rho. That this particular length, a small length, is in the direction of rho, and the differential quantity is d rho. And in the direction of z, if you are considering, that is this differential length we are considering, then the dl bar in the direction of z, which is equals to dz in the direction of z, right? These two are lengths, the differential length is satisfying. But consider the third one, that this is the third one what I am considering. The third one is not pure length, it is in the direction of phi. So what you have to do is you have to consider the length of that arc. If you have to consider that length of that arc, just you take the projection, and this small angle is phi, d phi. So in the direction of that phi, if you consider the small angle as d phi, then the length of this arc is nothing but radius multiplied with that angle rho d phi. So here clear, this is a simple point what you need to remember. We are not supposed to consider this one as a simple differential length. D phi a phi will not give us the differential length, that is the angle. So what you have to do is you have to convert this angle to the length with the help of this arc length formula rho d phi. So if you want to write down the differential length equation in the direction of phi, then rho d phi a phi is the component what we have. So clearly the differential length in rho direction is d rho a rho, no doubt about it, it is the length. In the direction of z, dz az, it is also a length, but in the direction of phi, since it is an angle and we are considering an arc, we need to take this one as rho d phi. So the general equation for the differential length now can be written as dl bar is equals to d rho a rho plus rho d phi a phi plus dz az. That is the differential length what we have. As I said, no need to go for the complex analysis. Once again, you can observe the differential length in the required differential surface in the required direction. So if you observe the direction initially, from this differential length you can observe or you can get differential surface. Now as an example, consider this surface. Now for this surface, as I said, the direction is always in the radial direction. The direction of this surface is in the radial direction, right? Now what is the quantity of this surface? The quantity of this surface is, that is differential surface is equals to, that is in the radial direction, the quantity is the length of this arc rho d phi, and this length is dz in the direction of a rho. So if you are considering this front piece, the front surface area, the direction is a rho and rho d phi dz is the magnitude. So if you rearrange this one, just it is rho d phi dz a rho, as it is I wrote here, no problem. Now check this one, that shortcut that what I gave. In which direction we require the differential surface? In rho direction we require that. So component rho will be closed. The remaining two, rho d phi dz were multiplied and a rho was added as the direction. In the same way, I will consider one more example. That let us consider this top surface. If we consider the top surface, the direction from our observation is always z direction. So what I am doing is I am considering the differential surface in z direction. So if you consider the differential surface in z direction, this length is rho and this length is rho t phi, right? This length is d rho. So here clearly the magnitude is d rho d phi is the magnitude of this particular surface what I am considering, and the direction is z, that is az. Now try to write on the same using our shortcut. In which direction we want differential surface? Z direction. So close this z. If you close this z, the remaining two terms are d rho d phi, and the direction is z. So in the same way you can write the differential surface equation for any direction in the spherical coordinate system or cylindrical coordinate system. So clearly what you have to do is you need to remember this differential length equation. So in the competitive examination, let's say whenever you want to recollect the differential surface area for the purpose of calculations, no need to go for this entire figure and take a part of this cake and analyze the what is this front surface or back surface or bottom surface. Just a little work, that the remembering of this particular differential length will give us a very good answer in an easiest way. So that clearly differential surface can be written in all directions. Now the differential volume, as I said, the differential volume is the combination of all the components, that this component, this component, this component, these three will be multiplied for differential volume. If you go for the geometry also, the same you will get. So the differential volume can be written as dV is equals to rho d phi dz. So simply the differential volume is a scalar quantity, differential surface and differential length. These two are vector quantities, right? Just remember our differential length and get the remaining all quantities in our cylindrical coordinate system. Now we will go for spherical coordinate system. Now we will observe the differential elements for spherical coordinate system also. For that, consider a sphere. In the spherical coordinate system, what we will consider is a sphere. So in that sphere, every point lies in our space. Now the base coordinate system is the rectangular coordinate system. With respect to that only we need to form the sphere. So form a sphere, and on the sphere consider a differential element. That what we are doing is we are considering a differential volume in that particular sphere. That imagine a piece of watermelon which is taken out from its surface. Whenever the watermelon piece is taken out from its surface, you need to imagine that particular shape. That if you take the watermelon piece, then it has one length which is cut along the radius and two arc lengths, that is one cut is along the theta direction and another length is along the phi direction. So if you imagine that one, then it is very easy to draw that at some location randomly I will consider that piece. Let us take, so somewhere I am considering the piece of watermelon like this. Let us consider a small piece of that watermelon, as I said, as a differential volume in our spherical coordinate system. This is the entire differential volume what I am considering. If you take the differential volume, if you observe the dimensions, this dimension is along radius, right, the radius of our sphere r, and this dimension is along theta, that with respect to the z axis we are considering the elevation angle. So this dimension is along theta and this dimension is along phi, differential phi. Now once again here what you have to do is we have to calculate the differential length in the direction of r, in the direction of theta and in the direction of phi. So here we have two angles, so those two angles must be converted as lengths. So if you observe the differential length in the direction of r, the differential length in the direction of r just simply can be written as the differential quantity in that particular direction dr ar, that this is the direction. And the differential length in the direction of theta can be written as that in the direction of theta, if you consider the length of this arc, what you will get is r d theta a theta, that is in the direction of theta, just it is r d theta a theta. And in the direction of phi, if you consider the differential length, that is r sin theta d phi a phi. So these are the differential lengths. The first one is the order of our distance, that is nothing but radius, and the second one is in the direction of theta, and the third one is in the direction of phi. So the general equation for this differential length now can be written as differential length is equals to dr ar plus r d theta a theta plus r sin theta, that it is r sin theta d phi a phi. That is the differential length what we have in our spherical coordinate system. Yes, I said once again we will go for the shortcut method, that instead of taking the differential lengths and multiplying them, if you want a differential surface in a particular direction, directly you can obtain that one from differential length. So as an example here, initially I will take the differential surface in radial direction. So differential surface in radial direction, close this term, then the component is r theta, here the component is r sin theta d phi. If you are considering the differential surface in r direction, then r d theta multiplied with r sin theta d phi. So the rearrangement will gives you r square sin theta d theta d phi. That is the differential surface in radial direction. As a cross check, we will examine for this case only that the differential surface in radial direction is like this. So if you are considering the differential surface in radial direction, this is the surface what we need to consider. So if this is the surface, what are the lengths of this one and this one? So multiply them, then what we will get is the magnitude. So the length of this arc, that is in the direction of phi. In the direction of phi, this is our length, that is r sin theta d phi, and the length of this arc, that is in the direction of theta, that is r d theta. And what is the direction of our differential surface? Obviously in the direction of r, that is ar. So if you take this one, that is r square sin theta d phi ar, same as our previous one. So in the same way, if you want to write down the differential surface for remaining all directions, we can consider this simple combination. So the differential surface can be obtained from differential length. Now what about the differential volume? As I said, the differential volume is a combination of all those components. That the differential volume can be written as the multiplication of this term dr multiplication with r d theta multiplied with r sin theta d phi. So if you multiply them, what you will get? Dr r d theta r sin theta d phi. So which is equals to just r square sine theta dr d theta d phi. This is the differential volume in our spherical coordinate system. So clearly observe, whenever you remember this equation once again, differential surface can be obtained and differential volume can be obtained. So clearly these are the differential length, surface and volume in all coordinate systems. What I do is, I will give you the comparison table. So in a table I will write all those components so that it is easy to remember. So all they will be taken from the differential length only. Remember that. So initially I will write the differential length and I will present the remaining all parameters. Just observe the comparison table of our differential elements in all coordinate systems. One by one I will present here. Let us consider the rectangular coordinate system. In the rectangular coordinate system, directly you can write the differential length. So the differential length is equals to dx ax plus dy ay plus dz az. So that is the differential length. As I said, just you remember this one, nothing else, right? Now in the cylindrical coordinate system, the differential length can be written as d rho a rho plus rho d phi a phi plus dz az. And in the spherical coordinate system, differential length can be written as dr ar plus r d theta a theta plus r sin theta d phi a phi. Now observe differential surface in all directions. Let us take the differential surface in x direction. dy dz ax, that is dy dz ax. Close this one and the remaining two components will be multiplied. The differential surface in y direction, close this one, dx dz in the direction of y. Just you observe, it's a one more simple concept. If you are considering in y direction, the differential elements will exist in x and y directions. And if you are considering x direction, the differential components will exist for y and z only, right? So if you are considering in x direction, you cannot find any differential element in the same x direction. Remember that point. In the same way, the differential surface in z direction, because blindly you can write this one as dx dy in the direction of z. You are considering in z direction, so the differential elements will be in the direction of x and y. So that we are integrating with respect, or we can integrate with respect to x and y. That's what we need to remember. In the same way, here the differential surface in the direction of rho. So if you are considering the differential surface in the direction of rho, the differential element which exist are phi and z. So the answer is rho d phi dz in the direction of rho. So the differential elements are phi and z. The differential surface in the direction of phi, which is equals to d rho dz in the direction of phi. The differential surface in the direction of z, which is equals to rho d rho d phi in the direction of z. I forgot to give you the differential volume here. Just write down the differential volume also. Differential volume is equals to, just it is dx dy dz. Here the differential volume is dv is equals to rho d rho d phi dz. So here in the differential length, one differential quantity is there. Differential volume, two differential quantities are there. Differential surface, two differential quantities are there. Differential volume, three differential quantities are there. So in any coordinate system, the same is applicable. So differential length, only one differential quantity. Differential surface, two quantities. Differential volume, three differential quantities. In the same way, so finish our spherical coordinate system also. So differential surface in the radial direction, which is equals to r square sin theta d theta d phi. Differential surface in theta direction, which is equals to r sin theta dr d phi. Differential surface in phi direction, which is equals to r dr d theta a phi. That these three will give us the differential surfaces in all directions, right? And the last one, differential volume. Differential volume is equals to the multiplication of these three, r square sin theta dr d theta d phi. Observe here also for differential length only differential element, it's a one differential element exists, differential surface 2 differential elements, differential volume 3 differential elements. Now blindly we need to remember that whenever we are supposed to calculate something with respect to this differential length, one integration will occurs. With respect to the differential surface, 2 integrations will occurs. With respect to differential volume, 3 integrations will occurs. So with this general knowledge, we will go for the definition of those integrations. They are called as integral operators on vectors. That whenever we have a differential quantity, that what we consider is a small or infinitesimal quantity, how to obtain something for the whole, that by integrating, that we need to apply the integration operation on our vectors. That before that integral operations, we need to learn what these are. Just we finished them, now we will go for the integral operations. Now we discuss about integral operators on vectors. What are different integral operators we have that can be applied on a particular vector? Let us consider a line. Now a field is passing through this line. Let us take a field A bar is passing through this particular line. If you want to observe how this particular field is passing this line, so what is the quantity of that particular field which is passing through this particular line? Then what we have to do is consider the differential length along this line multiplied with the vector what we have. Then what we get is the field which is distributed for this differential length only. Now if you want to obtain for the total length, then just integrate it from this point A to point B. That is called as line integral. That a line integral of vector can be obtained by integrating a particular quantity with respect to the line what we are considering. How that can be written? The line integration can be written as the integral line of A bar dot dl bar. Here wherever we are integrating, we can't integrate the vectors as it is. So what we have to do is you have to consider a scalar quantity, that this dot operation or the dot product will give us the scalar quantity for this A bar and dl bar. So if you are considering how this particular vector or this particular field is along our line, just a line integral can be calculated. If you observe, this line integral will consist of a single differential element. So if you consider that one in our rectangular coordinate system, dx ax, that is with respect to the dx only, we have to consider the integration. dy ay, or in spherical coordinate system, dr ar, d theta a theta, like that, only one integration will be there for this line. Right? So clearly remember that whenever we are integrating with respect to the line, just the integration is only once. Now in this line we have one more category called as closed line. This is called as an open line. That there is a ending for this one. That's A is started here, B stopped somewhere. Since we have two different points for the calculation, it is called as an open line integral. Now if the same line is taken like this, then it is called as closed line. That this line was started at point A and ended at the same point A. That's why it is called as a closed line. For this one also the principle is same, that the line integral will be considered along this closed line. The notation is like this, A bar dot dl bar. That what we need to consider. So it's open line integral as well as a closed line integral. In the same way, we have surface integral. Consider a surface. So whatever it may be the surface, just this is the surface what I am considering. Always the surface has a direction which is perpendicular to it, and for our mathematical convenience and evaluation, I will consider the differential surface over here. Let us take how much field is passing through this one. If you want to calculate it, then you have to calculate that field multiplied with this differential surface. Let us take A bar is the field. So if you multiply this particular quantity with the differential surface what we have, then that's you can observe how much field is passing through that particular differential surface. If you want to integrate this one, or if you want to calculate this one for total surface, we need to integrate it. That a surface integral can be defined like this, that a surface integral is a double integral. Since we have two dimensions, that the differential elements are 2. Since we have two differential elements, that will be integrated with respect to 2. That's why it is a double integral, surface integral of, once again we need to consider the dot product between the vector what we have and the differential surface. So a bar dot ds bar will give us a scalar, we are multiplying that function or we are integrating that function with respect to the surface what we have, so that the field which is distributed for the entire surface can be observed here. Now same as in our line integral, here also what we have is closed surface integral. Let us take, this is the surface what I am taking. If it is simply open, if you are closing that particular surface, then it forms a volume. So whenever we have a closed surface, if you want to obtain how much field is going out from that surface, that is called as flux. How much amount of a field is going out from that or passing through that particular surface can be obtained using our closed surface integral. That the closed surface may be represented like this. That closed surface has a three-dimensional structure and completely it was closed. Once again we need to calculate the closed surface integral like this. The notation is closed surface integral of A dot ds. So here whenever the open surface integral is there, just open surface integral, that is a simple plane will be calculated, on the plane will be calculated, and whenever the surface is closed, that along that closed surface we need to calculate the surface integral or the particular quantity. And the next one is volume integral. So what is volume integral? As we discussed, if there is any volume, obviously something is, if it is going out from the volume or if something is entering into the volume, we need to calculate how much quantity is going out or how much quantity is entering with the help of that volume integral. So let us take a volume. Now this is the volume what we are considering. To calculate the volume integral, we need to consider the differential volume within that particular structure. So this differential volume multiplied with the field what we have, then that gives the volume integral of this one. That the volume integral is a three-folded integral. Since the volume can be formed with a three-dimensional structure, that's formed as a three-dimensional one, it will have three differential elements. Since it will have three differential elements, the integration will be taken place with respect to individually. So that is a three-folded integral will be used, that is A bar dv. That what we consider here. Here there will be no dot product or cross product between them. Since dv is a simple scalar, just it can be written as A bar dv. Now here clearly remember that there will be no closed volume. If you are closing a line, a surface will be formed. If you are closing a surface, a volume will be formed. But if you are closing a volume, it's a no meaning. That a volume cannot be closed. So always a volume integral can be represented just like a three-folded integral of A dv. So these three are different integral operations on the vectors, that is with respect to the line or closed line, with respect to the surface or closed surface, or with respect to the volume.